All right, so get ready, because today we're taking a deep dive into a topic that I, personally, find completely mind-blowing, and that's the world of quantum mechanics.
Yeah.
We're basing our deep dive today on this great article, Understanding Quantum Mechanics in Simple Terms. And the thing about quantum mechanics is that it's like the bedrock of modern physics, but it describes a reality that's so different from what we experience in our everyday lives.
It really is. It's a world where, well, let's just say the rules of the game are totally different.
Right. Totally different rules, and that's what makes it so fascinating, but also, I have to admit, a little bit intimidating.
It's definitely a challenge to wrap your head around.
Exactly. So where do we even begin with something like this? I guess the first thing we need to tackle is this idea of wave-particle duality.
Uh-huh.
I mean, come on, how can something be both a wave and a particle at the same time? It just doesn't make sense.
Yeah, it's one of those things that just seems completely counterintuitive. In our everyday world, things are either waves, like think about the ocean, or they're particles, like little grains of sand.
Right.
But in the quantum world, things can be both. It's like a tiny little electron can act like a wave when it's traveling through space, but then when it interacts with something, it suddenly acts like a particle.
It's like it can't make up its mind.
Exactly. And the classic experiment that demonstrates this and really blew the minds of physicists back in the day is the double slit experiment. Have you ever heard of that one?
I have, but to be honest, I'm not sure I fully understand it.
So imagine you have a barrier with two slits in it, and you shine a beam of light at it.
Okay, got it.
Now, what you'd expect to see on the other side of the barrier is two bright lines of light where the light passed through the slits, right?
Makes sense.
But that's not what happens when you do this with electrons. Instead, you get what's called an interference pattern. It's a pattern of bright and dark bands, just like you'd see if you were looking at waves interfering with each other, like ripples in a pond.
Really? So even though they're particles, the electrons are somehow creating a wave-like pattern.
Exactly. It's as if each individual electron is somehow going through both slits at the same time. It's like each electron is interfering with itself.
So it's like the electron is in two places at once.
Well, that's kind of the weird thing about it. We can't actually know which slit the electron goes through without measuring it, and the act of measuring it seems to force it to choose one slit or the other. It's like the electron is in this fuzzy, undefined state until we observe it, and then it suddenly snaps into a definite position.
Hold on. Are you saying that the act of observing an electron actually changes its behavior?
That's what the experiments seem to suggest. It's as if the observer is playing a role in determining reality.
Wow, that's crazy. It makes you wonder what reality even is if it's dependent on us observing it. But okay, let's move on to another equally bizarre concept. Quantum superposition.
Right, superposition.
It's like that famous thought experiment, Schrodinger's cat, right? I know about that one.
Exactly. You're thinking about a cat trapped in a box, and in the box, there's a device that has a 50% chance of releasing a deadly poison. Now, until we open the box, we don't know whether the cat is alive or dead.
Right.
So, according to quantum mechanics, the cat is actually in a superposition of states, both alive and dead, at the same time.
It's both alive and dead. How is that even possible?
It's not that the cat is literally both alive and dead. It's that its state is undefined until we make a measurement, which in this case is opening the box.
Okay, so the act of opening the box forces the cat to be either alive or dead.
Exactly. It's the act of measurement that collapses the superposition and forces the cat into a definite state.
And Schrödinger came up with this idea to illustrate the strangeness of quantum mechanics.
Right. He was trying to show how counterintuitive these quantum concepts were when applied to everyday objects like a cat. And it's not just theoretical. Superposition is the basis for some pretty mind-blowing technology like quantum computing.
Yeah, that was my next question. Quantum computing is a big deal these days, and it relies on this idea of superposition, right?
Absolutely. In a classical computer, information is stored in bits, which can be either a 0 or a 1. But in a quantum computer, information is stored in qubits.
Qubits.
And a qubit can be in a superposition of both 0 and 1 states simultaneously.
Both at the same time.
Yes, just like Schrödinger's cat. And this is what gives quantum computers their incredible power. It allows them to perform calculations exponentially faster than classical computers for certain types of problems.
So superposition is more than just a thought experiment. It has practical implications for the future of technology.
Absolutely, and it's already starting to revolutionize fields like medicine, materials science, and artificial intelligence.
Okay, so we've got wave-particle duality, superposition, and now we have to talk about entanglement. This one, if possible, is even weirder than the others.
I agree. Entanglement is definitely one of the most mind-boggling concepts in quantum mechanics.
So what is entanglement exactly?
Imagine you have two particles, like two electrons, that are created together in a way that links their properties.
Okay.
Now, even if you separate these particles by a huge distance, like opposite ends of the galaxy, they're still connected in a way that defies our classical understanding of space and time.
So what you're saying is that if I measure the state of one of these entangled particles, it instantly affects the state of the other particle, no matter how far apart they are.
Exactly. It's as if they're communicating faster than the speed of light. But it's not really communication in the traditional sense. It's more like the two particles are so intrinsically linked that they're part of the same quantum system, even when separated by vast distances.
So it's not that information is traveling faster than light. It's that the two particles are somehow connected beyond our normal understanding of space and time.
Right. And this has been experimentally verified many times. It's not just some crazy theory, it's a real phenomenon. And it
Yeah.
has some pretty amazing potential applications.
Yeah, like what?
Well, for example, quantum cryptography, which uses entangled particles to create unbreakable codes. And there's also quantum teleportation, where the quantum state of a particle can be transferred to another particle instantaneously, regardless of distance.
Okay, now my head is really spinning. I need a moment to process all this.
Take your time.
So we've talked about particles acting like waves, existing in multiple states at once, and being connected across vast distances. Is there anything else that quantum mechanics throws at us that we need to know about?
Well, there is one more important concept that we should discuss, and that's the Heisenberg uncertainty principle.
Oh, yes, I've heard of that one. It basically says that we can't know everything about a particle, right?
That's a good way to put it. It states that it's impossible to know both the position and the momentum of a particle with perfect accuracy at the same time. The more precisely you measure one, the less you know about the other.
So no matter how good our instruments are, there's always going to be a limit to how much we can know about a particle.
Precisely. It's not a limitation of our technology, it's a fundamental principle of the universe. The very act of measuring a particle inherently disturbs it and affects its state.
So even with the most advanced technology imaginable, we'll never be able to fully pin down the exact state of a particle.
That's right. There's always going to be some inherent uncertainty in our measurements.
Wow, it makes you wonder if that uncertainty at the quantum level somehow translates to the uncertainty we experience in our everyday lives. I mean, if everything at the most fundamental level is uncertain, does that mean the future is truly open to possibilities?
That's a fascinating question, and one that philosophers and physicists have been pondering for decades. There's no easy answer, but it certainly makes you think about the nature of reality, free will, and the role of consciousness in shaping the world around us.
We touched on this earlier, but you mentioned that there are different interpretations of quantum mechanics. Could you tell us a little bit about the many worlds interpretation? Does that really mean that every time we make a decision, a new universe is created?
It's a mind-blowing idea, isn't it? The many worlds interpretation suggests that every time a quantum measurement is made, the universe branches off into multiple parallel universes, each representing a different outcome of that measurement.
So in one universe, I chose to have coffee this morning, and in another universe, I chose tea.
Exactly. In one universe, you might be a rock star, and in another, you might be a quantum physicist. It's a wild concept, but it's one way to resolve some of the paradoxes that arise from quantum mechanics.
Whoa, I need a minute to let that sink in. Parallel universes. So we've explored this strange and fascinating world of quantum mechanics. We've talked about wave-particle duality, superposition, entanglement, the uncertainty principle, and even the many worlds interpretation. It's a lot to take in.
It certainly is.
But even though it's incredibly complex and challenges everything we thought we knew about reality, it's also incredibly exciting.
It really is. It makes you realize that there's so much more to the universe than we can see or experience with our limited senses.
It's like we've only just scratched the surface of understanding how reality actually works.
Exactly. And that's what makes quantum mechanics so fascinating. It's a field that's constantly evolving, with new discoveries being made all the time. And who knows what amazing technologies or insights we might unlock as we continue to explore this strange and wonderful realm of quantum mechanics.
This deep dive has been truly mind-expanding. It's amazing to think about how all this weirdness at the quantum level ultimately underpins our entire reality. It makes you wonder, if everything is uncertain at the quantum level, does that mean the future is truly unwritten, a vast landscape of possibilities just waiting to be explored? I, for one, am eager to see where the journey of quantum discovery takes us next.